Welcome to the next topic of chapter 5, that is magnetic dipole moment of a revolving electron. So that way we proceed. That means the Ampere's suggestion that the real reason behind magnetism is the presence of circulating current. So inside the materials or the objects, what we have fundamentally, it is atom. Inside the atom there are electrons, and you know the electrons inside the atom, they are not stationary, they are in continuous revolution, just like what the planets, they revolve around sun. These electrons will be revolving around the nucleus. This model was suggested by Rutherford, and later that model was redefined, and it was well stated by Bohr in his Bohr atom model. So we take that model and we find the basic dipole moment of a revolving electron. So that is this topic, that is the magnetic dipole moment of a revolving electron. So when an electron revolves around our nucleus, what is the magnetic moment produced? That's what we are going to discuss now. So all electrons, they are revolving in different orbits in atoms. They have associated dipole moment for the magnetic field each electron creates. In the Bohr model, for the hydrogen atom with only one electron, the electron revolves around positively charged nucleus, just like the planet revolves around the sun. So we have the nucleus, this diagram, it shows a nucleus, and around the nucleus an electron is revolving. So here we have the most fundamental case, that of a hydrogen atom. It's written Zd at the center. For hydrogen atom, that Z is 1. So we have the hydrogen atom. In the hydrogen atom, that single electron is revolving around the nucleus. So when the electron revolves around the nucleus, the current produced by the revolution of the electron, it is in the opposite direction. So in the diagram, it is shown the direction of motion of the electron. So current due to that motion of the electron will be in the opposite direction. So what will be the direction of this magnetic moment and angular momentum, everything we will be discussing now. So we have in the Bohr model, we know the electron is revolving with uniform speed, and the uniform circular motion of the electron constitute current. The direction of magnetic moment is into the plane of the paper, and it is indicated by that simple cross there. Why it is into the plane of the paper? Magnetic moment direction is given by IA. Here I said the current is in opposite direction. In this direction the current is. So when you use your right hand thumb rule, okay, curl the fingers of the right hand in the direction of current, then your thumb you will be getting into the plane. So the direction of magnetic moment due to the revolution of electron in the hydrogen atom is into the plane of the paper. Now let's find the magnetic moment. So the magnetic moment is given by IA. The magnitude of magnetic moment is IA. So first of all we should find I. So here one electron is in motion and its charge is E. And in one complete revolution, for one complete revolution, let the time taken be T, capital letter T, the time period. So the current is given by I is equal to E by T. And we know what is time period. Time period is the time taken to complete one revolution. In one revolution, you know, the total distance travelled by the electron is 2 pi r, that is the perimeter of that orbit, where that r is the radius of the orbit, and 2 pi r divided by v. V is that constant speed with which electron is revolving around the nucleus. So we have T is equal to 2 pi r by v. That means perimeter by speed. So we have I is equal to, just substitute this T in the expression for I is equal to EV divided by 2 pi r. That is the expression for current. And this is current, and this is to be multiplied with area of that current loop we say, so that area bound by that orbit. Here, what is the area bound by the orbit? It will be simply pi r square since it is circular in shape. So, substituting for A, so we have the orbital magnetic moment we are representing by the letter mu. The letter mu stands for orbital magnetic moment, mu. Okay, so that mu is equal to EV divided by 2 pi r into that into we have pi r square. So pi and pi will get cancelled, one r also will get cancelled, and we will have EVR divided by 2. So that is the expression for magnetic moment of this current produced by the movement of the electron in hydrogen atom, that is EVR by 2. Now this direction of magnetic moment we already discussed, it is into the plane of the paper. Now we rearrange this equation. So we have EVR divided by 2. We are multiplying and dividing that right hand side with ME, where ME is the mass of the electron. So this equation comes like that, E by 2ME into MEVR. And we know MVR, the MVR is the expression, or it is the magnitude of angular momentum. You know, last year we have studied angular momentum. It is R cross P, where R is the radius vector and P is the linear momentum. And what is linear momentum P? P is M into V. So it is actually R cross M V. So in uniform circular motion and all, this R and V are perpendicular to each other. So magnitude of R cross MV, it becomes MVR. So usually in circular motion, the angular momentum has the constant magnitude MVR, where M is the mass, V is the velocity or the speed. Okay, magnitude of velocity or the speed, and R is the radius. So here MVR, ME into VR, it stands for the angular momentum of the electron, which is in circular motion around the nucleus. So we replace that MEVR with L, where L stands for angular momentum of the electron. So we have mu L, that L stands for orbital. I think you know such things from chemistry. L stands for that orbital and moment, magnetic moment, mu L. Mu L is equal to minus E by 2ME into L, where L is the angular momentum. So very important equation is this, which relates magnetic moment with the angular momentum. And the ratio of this mu L to L. So we have mu L is this. This is the expression for mu L. That mu L by L will give you a constant, and that constant is what? Mu L by L is equal to E by 2ME. So E is a constant, ME also is a constant, or the ratio of magnetic moment to angular momentum, mu L by L, that is what? That ratio is a constant, and that ratio is called as gyromagnetic ratio, and it is a constant. So gyromagnetic ratio is nothing but the ratio of orbital magnetic moment to angular momentum. That ratio is gyromagnetic ratio, and that is equal to E by 2ME. E by ME is nothing but the specific charge, that means charge to mass ratio of the electron, E by M. Usually we speak about this E by M. E by M in chemistry and all you have studied, I think. Who determined E by M? It was J.J. Thomson who determined E by M. So that E by M, charge to mass ratio, that's what it is referred as E by ME. So E by 2ME means it is half of the specific charge of the electron. So mu L by L is equal to E by 2ME. It is a constant, and that constant is called as gyromagnetic ratio. Now in this equation, in the first equation shown here, it is mu L is equal to minus E by 2ME into L. Here that negative sign shows that both orbital magnetic moment and angular momentum, they are opposite in direction. We already stated mu L is into the plane, so the direction of angular momentum is out of the plane. So that direction relation is shown by this equation with that negative sign. Here we deal with only magnitude while defining gyromagnetic ratio. So what is the value of that gyromagnetic ratio? That ratio is 8.8 into 10 raised to 10 coulomb per kilogram for an electron, and it has been verified by experiment. Okay. Now, this fact that even the electron is having a magnetic moment. So this calculations and all, we said this is verified, just mu L by L. So it shows that electron is having magnetic moment, and it confirms that Ampere's hypothesis that the basic reason behind magnetism is circulating current. So according to Ampere, we have that expression. That means we can find that fundamental magnetic moment of an electron in hydrogen atom. We reached up to mu L by L. From that we can obtain the expression or the value of mu L for one single electron in that hydrogen atom. What is the magnetic moment? How much is that magnetic moment? We can calculate that using Bohr quantization condition. This I think you have studied in chemistry. According to Bohr model of atom, the angular momentum will be integral multiple of h by 2 pi. We'll be studying Bohr model in detail in one of the chapters. In 11th or 12th chapter we'll be studying. There we have this angular momentum of the electron in an atom. It should be an integral multiple of h by 2 pi, where h is the Planck's constant. So here n can be only an integral value, just like 1, 2, 3, etc. Okay, and h has the value 6.626 into 10 raised to minus 34 joule second. And this condition only we call as Bohr quantization condition, and by this concept only the concept of quantization came. So first came the quantization of angular momentum, then only the quantization of energy came. Like that, that branch quantum mechanics itself, it evolved with this introduction. That means Bohr model. L is equal to nh by 2 pi. So that much important this equation has importance, that equation has in physics. L is equal to nh by 2 pi. Okay, so by substituting this condition, we have mu L. So we just put n equal to 1 because we are considering hydrogen atom. In hydrogen atom only one electron is there. So that principal quantum number n can be taken as 1. So when we substitute that value and we substitute for L, we'll have mu L is equal to E by 4 pi me into H. All are constant. E is 1.6 into 10 raised to minus 19. H is 6.63 into 10 raised to minus 34. Pi value we know. Mass of electron 9.1 into 10 raised to minus 31. All values are constants, and we get that mu L to be 9.27 into 10 raised to minus 24 ampere meter square. Okay, so that this is the fundamental magnetic moment of an electron in an atom, because we considered the hydrogen atom, and in the hydrogen atom only one electron is there. For that electron, its magnetic moment, orbital magnetic moment, is 9.27 into 10 raised to minus 24 ampere meter square. This fundamental magnetic moment is called as Bohr magneton. This is termed as Bohr magneton, and the value of Bohr magneton is 9.27 into 10 raised to minus 24 ampere meter square. So any change in the uniform circular motion would have an associated any charge in the uniform circular motion would have an associated magnetic moment. This dipole moment is called as orbital magnetic moment. And besides this orbital magnetic moment, an electron is having an intrinsic magnetic moment called spin magnetic moment. Intrinsic means by nature it is having a magnetic moment, and that is called as spin magnetic moment. And these things you will be studying further in higher studies, or in chemistry also you may be coming across. For us, what is our point of importance is this Bohr magneton. That Bohr magneton is the fundamental magnetic moment of an electron which is revolving around a nucleus. So with this, we conclude today's session. Thank you.